Let's take a pause and think conceptually about exactly what we've done here. And I'm going to show you it by using a pH volume graph, so otherwise known as a titration curve. So anyway, here it is from our pretty little computer. The vertical axis is pH and the horizontal axis is the volume of the HCl added. So you can see at 0, volume added, we have a rather basic pH up there, pH a little bit more than 11, because all we have in there is sodium carbonate, and this carbonate is a base. All anions are bases. Anyway, then I start adding HCl, and of course, as you would expect, if I start adding HCl, the solution's going to become a little more acidic, and that's because I'm doing a neutralization of the carbonate. Okay, so I add a little bit of the HCl, that little bit of the HCl neutralizes a little bit of the carbonate, so we get the NaCl being made, and then the H comes in with the CO3 minus, and so we're going a little bit down in our pH. Now we get to a point here where it starts shooting down a little bit more quickly. Now a lot of times in a pH curve you'll see this shooting down a lot more dramatically, and indeed we'll see dramatically in a minute. But what's happening here is that we're pretty much made all of the CO3 minus has become the bicarbonate here. Now you probably haven't heard the words conjugate yet, but the conjugate HCO3 minus is the conjugate acid of this CO3 minus. But this HCO3 minus is not just the conjugate acid of carbonate, it's also a base in itself. So it's an amphiphilic species. And because it's an amphiphilic, this sort of curve here, which would normally be a lot sharper, is somewhat poorly defined. Anyway, we keep adding in the HCl, and we're going to keep neutralizing now this HCO3 minus. And of course, as I hope you've learned in class, when you neutralize bicarbonate, or ultimately neutralizing carbonate fully, then you make water and carbon dioxide gas. And so this reaction is happening here. More acid in, more neutralization, more acid in, more neutralization, until I get to this point here where I've made, and I put this in quotes, H2CO3, and that's all that's in there. That's the water and the CO2. This carbonic acid decomposes to make water and CO2. You can see now that I've got this very sharp decrease as I go from a solution that's got a little bit of base in to now a solution which is just going to be acid, and I keep adding acid, and you can see that the pH continues to go down. Now this was a very rough way of doing things, but you can see that pretty much the amount of acid needed to neutralize the first carbonate to get HCO3 minus, a little bit over 6, is about the same as that needed to neutralize the second amount, going from a bit more than 6 to a bit more than 12. So this is what we're actually doing in there. Although the only thing that we can really do is we can look at the indicator. Now we chose methyl orange for an indicator, which is one that you haven't seen before probably, but methyl orange changes color between pH of 3 and 6.3, give or take. So there's the pH range for the color change of methyl orange, and you can see that it includes quite nicely this equivalence point, or this sharp point of the curve, thus letting us know when we've added enough HCl in there to completely neutralize not just the carbonate into the bicarbonate or hydrogen carbonate, but then the rest of the hydrogen carbonate. So anyway, to data. The mass of the sodium carbonate that I made up in 250 cubic centimeters of solution was the 2.7448 grams. You're going to need that fairly quickly. Then we're just going to have our data sheet here. We started with pipetting 10.0 cubic centimeters of this sodium carbonate solution. And what we found is that we needed 23.9 cubic centimeters to neutralize it to get into that methyl orange color change region that we showed there. Remember, we started at 0.2 and we ended up at 24.1, so we added 23.9 cubic centimeters. I did the experiment several more times. So trials 2, 3 and 4, I used 10 cubic centimeters of the sodium carbonate solution, and you can see that the amount of HCl that I needed, values all pretty much very similar, so the data are concordant, to use the A-level word that I really don't like. But then for trials 5 through 8, I thought, well, let's use a little bit more of the sodium carbonate solution. The more of this I use, the bigger these numbers are. The bigger these numbers are, the less the inherent error in measurement has an effect, and so it's always good to try and measure as large numbers as possible. So 25 cubic centimeters of sodium carbonate solution needed about 60, give or take, cubic centimeters of the HCl solution.